Hello and welcome everyone to another episode of the Reading Club. And in today's episode, we are going to discuss a very different type of topic, which is related to LP solving methods, right? So, MIP solvers nowadays also have interior point method in them, and in today's episode, we are going to explore this particular paper, which describes why do MIP solvers have any kind of interior point method for solving the linear programs. Okay, so what exactly is this interior point methods, right? So particularly we are going to talk about the barrier method which people use in their solvers. So this is first of all not a method to solve mixed integer programs, it's a method to solve linear programs. Okay, so we use LP based branched bound, and we typically solve our linear programs using simplex method, right? But there is also another method which is called barrier method, which is an interior point method that we can use to solve linear programs, right? So I'll just give you a small overview about what those things are doing, right? So we all know that we have our linear program and it is some sort of a polyhedron, right? So something like this, okay? And what simplex does is that it basically starts with one vertex and then moves to another vertex and then moves to another vertex and so on and so forth, right? So let's say if this is the objective direction, right, then it basically will stop at this vertex over here. That's the optimal solution. And as compared to that, what the barrier method or on all the interior point methods will do is basically they will start with the analytical center of this polyhedron, right? So somewhere over here. So it's basically like assume that all the constraints are pushing the variables to take farther value from their boundaries, right? So it will start somewhere over here and then it will gradually move towards this solution, right? So it will also again lead to the optimal solution, and so that's how it basically moves, right? So it doesn't really go through all this edge and corner points. It moves from center, right? So this is like a center path. Okay, so this is actually not really a good picture because this is a two-dimensional polyhedron, right? So I actually wanted to show the optimal face of the polyhedron, but I think we can show with even two dimension, right? So let's say that we have this kind of a polyhedron, and let's say this is also the direction of objective, right? So like this way, which basically means that this entire constraint, right? So this entire line segment is our optimal solution. So both of this solution, and pretty much everything that lies between these 2 points, all these solutions are also optimal solutions. Okay, so we start with this center solution, and then the barrier method will basically move towards over here, this center, right? So simplex will move from corner to corner, right? So it will, let's say, start from here and will go to here and then here. Either it will stop here or it will, let's say, stop here, right? Depending on what you want to do on degeneracies, right? So it will never really touch anything in between, right? So this is also a solution because it's actually in the optimal phase, and in higher dimensions it happens a lot, right? So this optimal phase itself can be seen as a polyhedron, and all these points inside this optimal phase are all optimal solutions. So we can actually sometimes benefit from having this kind of central type of optimal solution, right? So it's actually analytical center of this optimal phase that we get to using this barrier method. Okay, so yeah, that's just a different method of solving linear programs. It kind of uses Newton's rules for finding this solution. Basically converts the entire LP in a continuous function, and then uses Newton's method to find the minimal point, and that's how it basically reaches these analytical centers, right? And then depending on some parameters, basically certain values you change so that it converges at the end to this solution, right? The optimal solution, right? And when you have to find this solution, you have to also take into account the original objective value. Okay, so why do people actually use this, right? So first of all, it has basically some guarantees, right? So it is polynomial time. So polynomial, right? So it has running time which is polynomial in terms of the problem size, input size, right? Whereas simplex is not polynomial time algorithm, right? At least theoretically it is not polynomial time algorithm, and there are certain specific cases on which you can basically show that simplex method will take exponential time. Okay, so first of all, this one has polynomial time guarantees, and second, people mostly use simplex because even though it is not polynomial time, it works very well in practice. And there are, so like basically they were not hitting those extreme cases where simplex method will have to face this exponential running times, whereas basically like it is still an exponential time algorithm. So if you push hard enough, then eventually you will hit those instances where simplex is just too slow, right? So there is no clear dominance between barrier method and simplex based LP solving methods in terms of domination, right? So yeah, sometimes simplex works better, sometimes this barrier method works better. We never know which one is going to work better for a given MIP, right? So given linear program. So with MIP we basically solve all the linear programs, right? So and then we branch and bound. And so yeah, so what people do is that since this has guarantees and everything, and complexity wise it is kind of not super heavy, then they basically try all the methods in parallel, right? So they have simplex, and there are two versions of simplex, right? So there is primal simplex and there is dual simplex, and there is also barrier, right? So they basically run one thread on one thread they run primal simplex, on other thread they run dual simplex, and some other threads they run barrier method, right? So they run all of them in parallel when they are solving the initial linear program, the very first linear program, and then whichever one converges first, whichever one gives you the optimal solution, you basically use them, right? So that kind of sometimes this primal or dual simplex method wins, but sometimes they are just too slow for the problem. So in those cases barrier method wins, like it solves the problem faster. So this alone, like this is called concurrent LP, like so they use all these threads in parallel to solve the LP, and that itself, like presence of this barrier method itself can really reduce the solving time by a lot, right? So the initial LP solving time, so that is reduced by 36%, and that's what they reported in that paper, and the overall solving time is reduced by 4% overall, and this was all on MIPLib. Okay, I think MIPLib 2010, because last version was not released when this paper was published. So yeah, it's this is like mostly the gain is because of this, right? So initial LP they were able to solve faster, and that basically translated into finding faster the first solution, and then overall like minor gain. Like this is not really a minor gain, it's a big gain, but yeah, there is a direct benefit from using barrier method straight away, right? So that's like one reason. There are other things also, like we'll also see that it in other ways, right? So having this barrier method also helps with other components, not just the initial LP solving part. So we'll see that now. Okay, so the next part is in pre-solving. Okay, so there is a particular pre-solver which is called reduced cost fixing, right? So that's a pre-solving technique. So let's say if I have a reduced cost of my some of my variable x, and that is let's say greater than I have some objective upper bound, right? So this can basically come from an integer feasible solution, that minus pi transpose b, right? So what is this? So recall that we have our linear the integer program is C transpose x, ax equal to b. So this is what we are minimizing. This is constraint, and let's just say x greater or equal to 0. Okay, so pi is the dual variables for this constraints, right? And this is b, right? So when you have a reduced cost of a variable which is greater than this amount, so this can come from any feasible solution, right? So this is the upper bound on the objective z bar. So this is equal to z, let's say, right? C transpose x. Okay. And so in this case, basically we can fix x to 0 or its lower bound, right? So this is called reduced cost fixing, right? So this like requires you to know how simplex works and what is the meaning of all these things, but you can basically prove it, right? So in any integer optimal solution or any solution, LP solution, if x is taking higher values than 0 or its lower bound, in this case, after seeing this, then it will have the objective value which is higher than this, and you have already found an integer feasible solution with this objective, so you can obviously fix it to 0. Okay, so this is a pre-solving technique. You can also use this with simplex, right? So why use this particular pre-solving with barrier? Well, because you can, so we can use it, so of course. And second is that this barrier method, right, it gives you a it also gives you a dual solution, right? So simplex is not the only one which can produce dual solution, but barrier you can also find a dual solution. And with this barrier method, the dual solution has maximum number of non-zero dual values, right? So this pi that we obtain from this barrier method, right, it will have maximum number of non-zeros in it, right? So that's why this reduced cost fixing might work better. That's what they thought, and apparently they found that this pre-solving using this reduced cost fixing, it was actually performance neutral, right? So it wasn't really doing a lot, right? So not plus, not minus so much, it's basically neutral. Yeah, so that's one minor thing about pre-solving with this reduced cost fixing, but there is another thing that you can do, right? So let's say that we have, so this barrier method basically starts at analytical center, right? So over here, and when this analytical center we start with, right, so it has most number of variables that are away from its bound, right? So if x also has an upper bound, it will not take its upper bound value or its lower bound value, it will try to stay somewhere in between, right? So that's what happens when you use barrier method, because you tend to go to this analytical center, right? So in your polyhedron. But let's say we found this analytical center of the polyhedron and we found a particular variable, let's say x j, right, at its lower bound or upper bound, then what does that mean? That basically means that even though when we are trying to push things away from the boundaries, right, this variable still managed to get to its one of its bound. That basically means that in any feasible solution, right, so this variable will take that bound value, right? So this is true for any feasible solution. So what we can do is we can simply just fix this x to its lower bound. Let's say it took the lower bound value, then we can just simply fix it to its lower bound, and we can just remove it from the problem, right? So was this helpful? So they basically implemented it. The question is now, was this helpful? Not really exactly, because the thing is, like, directly when you, this is like a proof that this variable xj will take its lower bound value in all feasible solution. So even if you solve it with the simplex method, that variable will anyway take this lower bound value, right? So what's the point of fixing it? So first of all, it reduces the problem size, so that's one advantage. And second is that by fixing one variable, we can trigger more preprocessors, right? So preprocessors work like that, right? So when you change one variable or one bound or something, then some other preprocessor will get triggered, and then that will do some more reduction, and things like that will happen, right? So there they get some benefits because of this, right? So it's always helpful when you can fix something or reduce the bounds, and yeah. So that's how they used the analytical center, which you can find using this barrier method. for their pre-solving, right? And that basically did not really give a lot of improvement, but they say that in the paper it's 2% improvement. It's not a big improvement, but it's still noticeable improvement, and it's worth having if you care about it, right? So yeah, so that's a use of interior point methods in pre-solving. Okay, so the next application of this barrier method is in heuristic. Okay, heuristic. Okay, so we all know rounding, right? Rounding. So what is rounding? Right. So let's say if we have a variable x, it took the value 7.9, then we will just try to round it to 8 and see if that is still feasible, right? So that's how we basically, from an LP feasible solution, we try to find the integer feasible solution like this. Now what happens is this, right? So we have our polyhedron, nice little polyhedron, and let's say we are here or over here, right? So when we try to round things, right, so we are very likely to move out of this feasibility region, right? So we'll end up here or anywhere, right? So all these directions are possible, right? And whereas what happens if we try to round this solution, right, the analytical center solution? So it's likely that we'll still stay in the feasibility region, right? So that's called center rounding, right? So this, when we try to round this analytical center solution, we are likely to still remain in the feasible region, and so we are more likely to find an integer feasible solution when we try to round this one. So that is one heuristic, right? So that's a very simple idea. All you need to do is basically the same thing, like the rounding only, but apply it on the analytical center solution, so it works better. But people actually tried something more than this. Okay, so let's say that I have some solution in which my x1 is taking, let's say, 0.8, x2 is taking, let's say, 0.7, and normally with this type of rounding, let's say I have this analytical center, they can just simply round this one to 1, also this one to 1, and see, and basically keep going like this, and eventually they will basically see if this is feasible. In a lot of cases it will be feasible, because you try to round the analytical center solution, but sometimes it may not be feasible. Even when you move from central solution, you might move out of the feasibility region because something went wrong, right? So what they did was called soft rounding. It's kind of interesting. Okay, so what is this? Okay, so let's say, first of all, let's say if I have one more variable, let's say xk, it took 0.9999, something like this, then basically it's kind of obvious that this should be fixed to 1, right? So basically they fix it. If something is very, very close to an integer value, then they fix it to 1. But other variables like this one and this one, they don't fix it. This is they try to round it, but not hard rounding. It's a soft rounding. So what is soft rounding? So they basically discard the original objective, and then they basically add this kind of objective. Let's say it is maximize 0.8 x1 plus 0.7 x2 and things like that, right? So what exactly this objective is doing? So this objective is pushing this x1 to take value 1, right? So it is pushing in the upward direction with coefficient 0.8, and this one is also pushing this x2 variable to take value 1, but which has a smaller coefficient. So these coefficients, right, these objective coefficients, they are proportional to their analytical solutions values. So if it is very, very close to 1, then it will be pushed higher, pushed even like strongly towards that solution, whereas if it is like far from that rounded solution, then it will be pushed not so much, right? So that's it. They don't really use the exact numbers. They just say that it is proportional to this this number. So I just used as it is for now to explain things. But yeah, that's the idea, right? So why so what's the next step? Like, so once we have this kind of an objective and we have like some variables fixed, we basically solve a submip, right? So if in the hard rounding, if it is not working out, then it is likely that in this soft rounding, when we are solving this submip, when we are trying to round it to that values, but we are not forcing it, we are just pushing it, so that way we are more likely to find the feasible solution. Okay, so this is another heuristic which kind of uses this analytical center solution. Okay, so this is an expensive heuristic. Expensive, it's very, very expensive. So we were basically solving a submap, so it's super expensive, and also we basically need to find this analytical center for this. So these people, which are like basically they implemented all those things in Express Solver, they don't use it very frequently, they use it rarely, right? And even in that case it brings big improvements, right? So particularly there is one benchmark by Hans Mittelman, it's called the feasibility benchmark, and on that particular series, that particular benchmark, they said that they observed 40% speed up, right? So that's a big speed up, but like on a very specific case, right? So it's when your problem has certain type of structure and it is very hard to find feasible solutions by other methods, then this particular heuristic can come to rescue, right? So yeah, that's another use for using this barrier method and analytical center solution. Okay, so the last use is in branching, right? So typically we use reliability branching or pseudo-cost branching or strong branching or those kind of branching rules, but they have another branching rule which is called analytical center branching, right? And they use it only in specific cases, very rarely. Okay, so which is the specific case is that when we observe very high degeneracy, when we solve LPs with simplex and we observe a lot of degeneracy, right? So that's when people use this branching rule, and they only use it at the top of the tree, right? So this is like very rarely used. Once we have something reasonable, then they basically switch to this normal branching rule, right? So pseudo cost or reliability branching or something like that. Okay, so what is exactly this branching rule? It's kind of basically the same idea that we have been discussing, that this analytical center solution, right, it is supposed to be in the center. So if something is close to their boundary, some variable, let's say some binary variable, right? So this variable is close to 1, right? In that case, it is very likely that it will be 1 in the optimal solution as well. So basically we try to branch on this binary variable. So there are very few of those variables, and the idea is that it is supposed to be near the center value, right? So near 0.5, but it is not really near 0.5, it is very, very close to its bound, even in the analytical center solution. So that means like in the other solutions, feasible solutions, on even the optimal solutions, that variable should be close to 1 or pretty much 1, then we basically explore this variable first for branching, right? So they branch on this variable and they also explore the up branch first. So this is the node selection rule. Okay, so if at all we want to explore the subtree that is generated by branching on this variable, then we have to explore this up branch first. So that's the idea behind branching. Again, like it's we have been discussing the same idea. So whether is it helpful or not, it's actually first of all very rarely used, because they only use it when it is like super hard to solve and they detect that very high degeneracy is there, and on those cases they use this kind of branching, and that also only at the top, so very rarely applied. But when it is applied, it is kind of very beneficial, right? So it is that's what they mentioned, and so that basically leads to like 2% speed up overall in entire MIP lib, right? So that's use of this analytical center solution in branching, and that's why they have this barrier method. Okay, so to conclude, like what all things we saw, right? So first of all, it's an LP solving method, right? So this barrier method, interior point methods, they basically directly help with the LP solving part itself. The first thing that we saw, right? The concurrent LP, that's what they use it in. Then we saw its use in Presolve, right? So we saw how to use these things for reduced cost fixing and other kind of pre-solving techniques for variable fixing. We saw one heuristic, right? Heuristic, which is based on the interior point method, the analytical center solution, and they also described one branching loop. So in all those cases, we saw heuristic branching. This interior point method was helpful, right? So this is why they have it in the MIP solver. And they also mentioned a few things that they did not describe in this paper, which is it is kind of used in helping feasibility pump. This is a common, very famous MIP heuristic, right? So for finding integer solutions, and this feasibility pump also can make use of this interior point method solutions. And there are also some cutting planes method that they did not describe, but they have references for this. So they also make use of these interior point methods. But yeah, so overall it's kind of I now have answers. I'm understanding about why MIP solvers actually have this use this interior point based methods, barrier methods, and mostly they use barrier method, but why at all they use it, even though they have like simplex methods, right? So there are lots of use cases that we have seen, right? So that's pretty much it. If you want me to cover any of these two parts, particularly I have they basically gave references in that paper, so let me know in the comments. I can cover it in next videos, maybe this one or this one. But yeah, that's all for now. Thanks for watching. Don't forget to like and subscribe. So yeah, we'll see you in the next video. Bye.